Hello again. So let's look at the Kleisli now you try exercise, where we're asked to show that for every monad we get the functor from C, which is the category the monad is on, into the Kleisli category of M. And the point of this exercise is to get used to the category solver, which does all of the boring things such as dealing with identities and rebracketing association, compositions, etc. Because we already defined what the functor is. It's the identity on objects, and it's composing with return on morphisms. Okay, so let's see if we can do this. So the first thing we have to prove is that this preserves identities, which means that if we take the identity and pre-compose with return, then we should just get return, because that's how we define the identity in the Kleisli category. Right. Okay, so because all we need to do is we need to get rid of this composed with identity, that's something that the solver can just do like that. And that's basically for free for us. So that was easy. What about this one? So this is preserving composition. So if we take a composition and we embed it by composing with return, that should be the same thing as the composition in the Kleisli category, which is this much more complicated thing where you join and you f-map one of the morphisms. So here's the embedding of G, here's the embedding of F, and then you f-map over their composition. So this is where we actually need to use the solver, and where we're going to be thankful that we have the solver. So I think the first thing we do is we start from this side, for example, and we copy that, and then we just remove all the brackets, because the solver can do that for us. Then we reload, and we check that this was okay by just using the solver like this. So that was okay, and we can do the same thing starting from the other side. So we have this complicated thing, and now let's just remove all of the brackets. Okay, but then here we see that we have a functor which is applied to a composite, so we can just distribute that, so we can do the composite of the functor applications like that. I think that should still just work with the solver. Otherwise we've done something wrong. Okay, so these are the kind of trivial boring steps we can always do without thinking, but now we actually have to think. So we have to look at this expression and this expression and see if we can simplify one to the other. And I think in this case it's much easier to work backwards from this complicated thing and see if we can simplify it to this simpler thing. So let's do that. What do we have? Well, we know that join and return satisfies the laws of a monad, and we know that join and return are natural. So we can go and look at the laws for a monad and see if we can spot something. So we have that join followed by return is the identity, join followed by f-map of return is the identity, and join followed by join is something. And what do we have here? Well, we do have join after f-map of a return. Right, so let's focus on that bit. Property focus here. Okay, and then let's see if we can simplify that bit. So we said that a join after f-map of return should just be the identity. Okay, so that means that we should be able to replace all of this with just syntactic representation of the identity. Okay, and now here we actually have to do some work, right? We can't just say solve cat raffle. So we're going to reduce the goal, and we see that there's going to be two pieces. There's this piece where, okay, that was a mistake to normalize that fully. We have this piece where we actually have to prove these are equal, and then we're going to have a bunch of boring pieces where we can just say RD, and it's two more boring pieces. these. So these things are outside of the focus. The things are still pointwise just equal, right? But here in the focus we say RQ, we say qualitative, and now we need to prove this. But the point was that we had the map return join function, which is still all we need. So it's map return join of M, and then if you look at that, it looks like it's the right thing, but we should sim it. This is going the wrong way around. Okay, so that's a bit easier, right? And now let's see what else we can do. So the first thing we could do is we see that here now we have identity composed with something. So we know that we can always just get rid of identities. Solve cat raffle. Okay, so now we have a much more manageable expression here, right? So we want it to look like this one. And we see that the problem is that this return, they are on different sides here. But that looks like a naturality thing, right? We have an F map and then a return on this side. We should be able to switch the return over if we use to, if return is natural, which it is. So I think I'm going to put the focus here, because this is what I want to work on. And the solved cat raffle is still going to deal with that focus for me, so that's fine. And then here I want to turn them around, so I want to have a return on this side, and then something else on the other side. Okay, and I can look up here and really hope that it's just going to be G. I think it is, because return is a natural transformation from the identity to the monad. So this is, strictly speaking, it would be fmaps in of the identity functor, but that's just going to be returning its argument. I think it will be like that. And then after that, this step is easy, right? It's the same. So we just have to focus on this step, which again we can reduce the problem to two subproblems. We have the one where we actually care about things. Then here we have a simple problem, which is just by definition. So here we have a qualitative problem, and we have to show this. So what does it say? Well, we said that we wanted to use the naturality of return. So we have return nt on M. That's the return natural transformation. So we use the fact that it's natural. Then I have to give the actual functor that I'm natural with respect to here. It should probably be G, right? Oh, do I have to give two objects first? Let's see what I have. Yes, I have to give the X and the Y. So I'm just going to give underscores for these, and hopefully I will infer them for me. And then I want G. And then what I have indeed looks like what I want in the goal. And it's done. So I could use the solver to focus on the bits that's really important. And that way I managed to finish this, which would have been a pain if you had to do this by hand. So I hope that was helpful.